Hey, what's up, YouTube? We're back. Today's July 28th, and we've got another episode in our series learning basic mathematics. This really terrific, pretty little yellow book by Serge Lang. Love this book. If you are watching this series, this is episode 6. You're welcome to just watch this if it's the first video that you're finding, but you will benefit if you've seen the previous videos first. But really, it's up to you. All of these videos are kind of self contained. My thesis that I want to give people is that math can be a hobby, dude. Math is fun. Math can be something that you study just for yourself, just for fun. So, yeah, let's learn math the right way. Like, let's relearn math. This book is Intro to Real Math, Intro to Proof Based Math for, like, in the context of high school pre-calculus, which is so unusual. It's so unusual, and I'll talk about this again and again, but let's keep moving. Today, we are jumping all the way forward from chapter 1 to chapter 16. We're going to jump to the middle of the book, and we're going to talk about an interlude, a really nice little interlude by Lang. And we're going to be talking about his thoughts on reading books. And then we're going to learn a little bit about logic, and then following that, we're going to work induction. And I'm going to teach you about the method of induction. Specifically, we're going to be revisiting the proof from episode 1, Gauss's proof revisited today. So let's go. Luna is not here. She's sleeping, but I guarantee you that she's going to show up again at some point because that's what she does. So don't worry, she'll be here at some point. Chapter I, the interlude on logic and more. So in this chapter, there are 5 sections. Today in this video, I only want to talk about and introduce sections 1 and 2. Section 1, on reading books. Section 2, on logic. These are going to be the 2 topics that I want to talk about first. Then we're going to talk about induction and summations. Well, really, chapter 16 is induction and summations, but I only want to talk today about induction. So it might get difficult sometimes to follow this series of videos as a course, but sorry, I don't know. I need to bounce around somewhat as I go, and we'll talk about that in a second. But a benefit about YouTube videos is that you can pause. You can pause the video and you can go read the section right now. If you weren't reading ahead and predicting that we'd get to chapter 16 next, well, here's your chance. You can go read it first if you want to. I encourage that, in fact, to read the section before you watch these lecture videos. I really do encourage it. Just so you know, the other sections in the interlude are about sets and elements, indices and notation, and the other sections in chapter 16 are on summations and geometric series. Beautiful stuff. You can read that if you want to, but we are only focusing on these yellow highlighted sections. Okay, so let's keep going. Section I.1. Oh no, my iPad is almost out of batteries. On reading books. Dude, I think that this section is marvelous. When I read this section, like, Lang is just he's a funny, wry, clever dude. Like, one of my private tutoring students called him sassy. Like, he's very sassy. And yeah, he is pretty sassy. I love his writing a lot. So when I saw that he has a intro to proofs for in pre-calculus, I was like, dude, that's all. Yeah, let's do that. Okay, on reading books. This part of the book, interlude section I, or chapter I, the interlude, it's like on page 90 or something. This book part of the book can really be read at any time. We could have started the very first section, the very first lecture that I had done could have been from this interlude. Or we could have done it later, or never, or early. Like, you really should read this part, but it's an interlude that the teacher can construct in a course, or at the self-studier, if you're reading this book on your own, you can read this part whenever you feel ready to. And I think that he says that in the preface. This book is about gaining mathematical maturity. There's this like vague, weird term, and it's very nebulous, but we're trying to grow up into mathematical adults, which is such a cool opportunity to blend with parallels of you can study math as a hobby as an adult with more maturity. Coming back to math for fun, you can learn it. You can learn like adult math, like the real math that we teach in college. Um, it's not harder. It's just different. And in my opinion, it's much more beautiful. It's much prettier. It's much nicer. If you've always wondered why the mathematical patterns work, that's what this book is teaching. It's about the concepts of math. So this part of the book can really be read at any time. There are many ways, he insists, of reading a book. There are many ways. Oh no, there's this one issue. This one should have been on. Oh well, that's fine. Minor mistake. Many ways of reading a book. So there are many ways of reading a book. I kind of want to jump forward and say that the courses take a safe path. Courses, traditionally, when you take a college course, or in high school, they take a very safe path. You do chapter 1, then chapter 2, then chapter 3, then chapter 4. Every section, one at a time. You work a bunch of exercises from this section, then a bunch of exercises from the next. And we follow this linear path. Like we're learning math level 1, then level 2, then level 3. And you never go back and revisit. That's a lie, dude. They lied to you in high school. That's not how math really works. In truth, in math, we work in the middle, and you work and you try to understand some sort of topic. You want to learn some topic, and you learn just enough to realize, oh, I need some foundations. I need to go back and learn some foundations and pull something from the foundations, and then I can apply this knowledge to something in the future. So Lang really recommends this, that you should really work from the middle and kind of go outward, like to foundations before and then applications after. And he gives this example that geometry can really motivate algebra, that like while you're learning algebra, you should be learning a little bit of geometry so you can immediately see when algebra is being used in something else. I think it's such a cool, clever idea, honestly. That's what we're doing here. I'm really taking his invitation to get weird. Like, please try experimenting, he says. Get weird with it. This is our path that we're doing at the moment. We went section 1, section 2. Then I added something from number theory. I added some facts from a number theory book that are not even in this book. Like Gauss's proof of adding those two lists of numbers, that's not in this book. But I pulled that from somewhere else that I know. Then we went to section 3. Then I added something else I know about from number theory. Now we're jumping to section 14. Then I'm going to show you section 60. And who knows what the next video is going to be, right? But like he's saying, follow your interests. Like, especially if you're a self-studier. If you're studying math on your own, you're allowed to jump around. And you're allowed to learn different sections at different levels of depth based on your interests or what serves you and your goals. So that's the approach that we're taking right now, jumping ahead to this section on logic. So section I.2 on logic. Throughout math, we need to keep clear what are our assumptions and what are proofs. Like, what things do we take as an assumption really kind of pulling back to foundations. Like you can assume some previous mathematical result is true and then work from there. You can assume that the Riemann hypothesis is true, then these other things must be true afterward, as an example. But we keep clear which things are assumptions and which things are results based on assumptions. At all times, we're trying to keep in mind what's assumed, what's a proof. Proofs are a sequence of statements. Like in this section, we want to understand a little more clearly what is a proof? What is exactly a proof? Like as a mathematical object itself, even. I haven't been too strict or rigorous about this yet, and I don't really feel like getting super rigorous with it either. But we do want to learn just a little bit about the theory of proofs itself. What is a proof? What constitutes, what is a good proof? What is a bad proof? Things like that. Proofs are a sequence of statements. This is a good working understanding that we've used for thousands of years. Proofs are a sequence of statements. Each statement is either an assumption, we assume that two parallel lines will never cross, or another statement can be following previous statements by a rule of deduction. In other words, we can call that common sense. Like in this book, our rules of deduction, we will just think of as this is just common sense. If this and this, then that. Let's give some examples of common sense deduction. And in this lecture today, my goal is to share with you all a couple of methods of deduction that you've probably seen, and then one method of deduction that you probably have not seen before. So, example one. This is a classic, man. This is a classic. All men are mortal. Okay, I could change it to say all people are mortal, but we've always said it this way. So all men are mortal. Socrates is a man. Therefore, Socrates is mortal, right? This is a logical argument. If we assume, let's just believe that all men are mortal. Let's believe that. And if we also believe that Socrates is a man, then it must be true, following those two previous statements, that Socrates is mortal. I don't have to take the previous two as assumptions. Maybe they're proofs somehow, like maybe I've proved it somehow in the past or not. It doesn't matter. From this point, we can conclude that Socrates is mortal if we assume the previous two statements. This is a classic example of a logical deduction. You take two assumptions and then you deduce a result from the previous two. All right, next example. Dude, I love this one. I'm pulling this from both of these, honestly, from this other book. So if the material I'm working is a little too easy for you, trust me, I got other recommendations. I can give you harder books on the same material. So if anybody wants recommendations, this is a terrific book on a mathematical intro to logic by Enderton. So this one is credit to Enderton. And what's cool is that this is the exact same proof structure. A1, A2, therefore A3. It's slightly more complex, but Borogoves are mimsy whenever it is Brillig. It is now Brillig, and this thing is a Borogov. Hence, this thing is mimsy. Man, when I read this, it made me so happy. When I saw this the first time in college, I was just like, that's so good. That's so funny and awesome. So you might be asking yourself, what the hell is a Borogov? What is mimsy? What is Brillig? And the answer is exactly. That's the point. If you believe whatever the heck a Borogov is, that it is mimsy, whatever that means, whenever it is Brillig, whatever that means, there's something called Brillig, there's something called a Borogov, and if a thing is, whenever it is Brillig, then Borogovs are Mimsy, and it is now Brillig, and this thing is a Borogov, therefore this thing is Mimsy. This is a logical argument, and it's the same structure of two assumptions and a conclusion. Now, these two assumptions are just slightly more complex, and if you want to have some homework to try to understand a little bit more here, A1 is kind of can be broken down as this first fact, and then A2 is a combination of other previous claims, and then therefore our conclusion is B2 and B3. Don't worry about that. I don't even know if I got that exactly right. It could be written slightly differently. Let's move on. Another example. Now, this one is by Lang. So now we're back to the math world. If 2x is 5, then x is 5/2. In math, we often, when we're doing these calculations, we just write a bunch of equalities, or we say this and then write the solution. But in math, those are really all if-then statements. If 2x equals 5, then x is 5/2. This is of the form, this is an argument of the form, if A, then B. So A, the statement A is 2x equals 5. Let's assume that 2x equals 5. Then it's logically a result that x is 5/2. So this is of the form of a deduction. It's just a direct implication. In this example, the converse is also true. If x is 5/2, then 2x equals 5. So in symbols, we can say B also implies A. A implies B, and B implies A. Both directions. So that's what the converse of a statement is. If I say A implies B, then the converse is the sentence, whether or not it's true, that B implies A. We'll come to some examples in a second. Thus, we say 2x equals 5 if and only if x is 5/2. These two sentences, 2x equals 5 and x equals 5/2 are, in some sense, equivalent, assuming that x is in the rational numbers and some other things. But if and only if, Lang doesn't use this term. He really, really prioritizes full English sentences. But you will see this is extremely standard and common. IFF means if and only if. A, if and only if B. Confusing thing is A if B really means B implies A, and then A only if B is A forward arrow B. Just don't worry about it. The only two forms that you need are if A then B, and A if and only if B. Nobody really works with only if as its own term. Don't worry. Let's just keep going. Next example. If x is -3, then x squared equals 9 is a true mathematical sentence. It's a sentence that's either true or false, and we believe it's true. If x is -3, then x squared is 9. And we can prove it based on the laws of arithmetic that we've built so far. Addition and multiplication of numbers. But I want you to pause at every point here. The reason I have these hidden is so that you can have a moment to think about what's next. The converse is false. The converse of this one is false. Why? Pause the video right now. If you don't immediately see it, think about it. Think about it. Why is the converse false? In fact, I'm going to leave it there. I'm going to leave that. If you don't see it, I want you to keep thinking about it because I think you'll find it. All right, example. Revisit now Gauss's proof, a constructive proof. Now, I don't want to leave that detail out because you can pause the lecture. You can pause this video, which is a great feature. x equals 3 also satisfies x squared equals 9. So the converse would say, if x squared equals 9, then x is negative 3, but that's not true. If x squared equals 9, then x equals negative 3 or x equals positive 3. There's two solutions to x squared equals 9, right? All right, now let's keep going. Example. As I said, we're going to revisit Gauss's proof. And this time we're going to see it as a little bit more carefully written as a constructive proof. First, this is our only assumption, actually. Let's assume that n, capital N, is 1 plus 2 plus ... n, lowercase n. Maybe I should have used S. I really like capital and lowercase n on this one. That's probably a mistake for me. But in any case, let capital N equal the sum of n integers. Therefore, it's logically true. This is by facts that we've proved already, commutativity and associativity, we can write n backwards as well. Then, n plus n equals the previous way we wrote n plus the new way that we wrote capital N. Right? So, n can be written this first way, and we write it right here. And then it can also be written this other way, and we write it there. That's another way to write n plus n. Then, therefore, definition of n plus n, or definition of 2 times a number would be n plus n. 2n equals this. I'm kind of jumping ahead, but I'm doing a commutativity. I'm using commutativity to rearrange the terms from the second large term. My Apple Pencil's broken today, so this may not work, but notice I'm moving this first lowercase n to be, I moved it using commutativity. I'm rearranging all of them in the same sort of way that Gauss's proof, when you add them, the two lines. And then, therefore, there are n of those bracketed terms on the right, and every one of them equals n plus 1. Therefore, capital N is n times n plus 1 divided by 2. So this is just a different presentation of the same exact rigorous proof that we showed in episode 1. But now it's written a little more organized, cleanly, as a constructive proof. Okay, so there's some examples of the first rule of deduction, which is just a direct implication. Another rule of deduction is the method of contradiction. How are we on time? Dude, I don't know. I gotta move faster. Another rule of deduction is a method of contradiction, also known as reductio ad absurdum. Somebody said reductio leviosa, and I thought that was really funny. So credit to Arad for that one. Reductio ad absurdum is reduction to the absurd in Latin, something like that. You make some assumption, and then you derive something that's absurd, a nonsensical fact. Then you know that your assumption was wrong. Classic freaking example here. I think, therefore I am. This is credit to René Descartes from the 1600s. This is exactly the logical method of mathematical proof and argumentation, the axiomatic system. René Descartes wrote this philosophical treatise called the Meditations in the Renaissance, making the argument that we can prove the existence of the external world, we can prove the existence of God and other things like that by using the mathematical axiomatic system. He had this incredible idea of hyperbolic doubt to reduce all of your assumptions and like even if it's the weirdest counterexamples in the world, like a demon is controlling your thoughts, or that I'm dreaming within a dream, therefore I can't trust my senses. Like maybe I'm just dreaming right now. Maybe I'm in the Matrix, bro. But what if I imagine that I don't exist? Like, what if I don't exist? Wait a minute, that's absurd. That's impossible. To Descartes, that was the bedrock, the only axiom that he could not relax to a previous axiom. To Descartes, if he imagined that he didn't exist, that would be impossible because he's currently imagining that he doesn't exist. So that is impossible. Something is happening. I'm imagining that I don't exist, therefore I exist. So I think therefore I am comes from this classic philosophical treatise. And it's exactly trying to use the language of mathematics and the mathematical methods from Euclid and the Greeks to try to apply it to building a full philosophy. He wasn't very successful, but this idea was excellent. This idea still stands the test of time. Another classic example that Lang gives, to get back to math like numbers, square root of 2 is irrational. He says that we've seen this previously, but I haven't shown you that. We haven't defined what square root of 2 is. Try it yourself, man. Like, this is an opportunity that I never had when I was learning math, because I was always learning it in a college classroom, and you have to rush and get through all the sequences, all the sections, and I wasn't a good enough student to read ahead. Try it yourself. Just from what I've described right now, what would it mean for square root of 2 to not be irrational? What does that mean? So you're going to imagine that square root of 2 is not irrational, and then try to find an impossibility, a contradiction, like a reductio ad absurdum, a reductio leviosa. If you get stuck, you can read this in the book. If you get stuck, and you probably will, that's fine, but set a 10-minute timer and try it. Like, don't rob yourself of that opportunity, because you're an adult, or you're a kid and you're studying math for fun. Like, we're studying for fun, so don't rob yourself of this opportunity. Try it. Try to figure it out. And let me know in the comments section if anybody proves square root of 2 is irrational on your own without having seen it before, because that would be truly an achievement for me as a teacher, because we don't usually teach it that way. Definition. Another important rule of deduction is the proof by induction. This is a little confusing, and it's a little unfortunate because I don't want to get into it, but the two words sound different, like as if proof by induction is not deductive. That's false. Proof by induction in math is a rigorous, formal method of deduction. It is a fully rigorous technique, but it feels like something called induction, which I'm not going to get into. Analogy. Everybody explains this one by analogy. You can try to define it formally, but it's just very messy. Nobody defines this, I think, in a lecture formally for the first time. Everybody uses this example, which I'm excited to share with you today. Right here, I think we're already in some math that some people have not seen before as adults. I think here is where we're going to introduce our first truly new idea that I think a lot of people have never seen before. And so I'm very excited to share this with you all. At this point, we're jumping to chapter 16. Right now we're in chapter 16, section 1. Analogy. We're going to define this by analogy and try to make it slightly more formal as we go. Think of dominoes. Think of dominoes. If you're in the US, think of the toys, not the pizza. Not pizza. This analogy really doesn't work for pizza. it would work with math books. This is stupid, but if I just did this for a second, my parents just shipped me like a giant box of math books from college. Um, and that made me so happy. Like I finally have a bunch of math books that now I need to get a new bookshelf or something. So this works if you imagine dominoes or math books stacked together. So right here, imagine that we have a bunch of math books or dominoes all stacked together neatly in a row, right? Now, imagine that Luna shows up and she loves to knock stuff over because she is so freaking cute and annoying and also adorable. If you watched my last episode, there was a funny moment when she just like loudly knocks something off of the desk. She's broken so many coffee mugs. She just breaks everything. So there's a bunch of beautiful math books all stacked together very neatly, and she knocks over the first one, right? If those books are close together, each one is going to knock over the next one, right? Like the first one knocks over the second one knocks over the third one knocks over the fourth, etc. But if there's a gap, then one of the books falls over, but then the other ones don't fall over, right? Pretty reasonable. The method of induction, let me remind myself. Yeah, let me try to explain it here. The method of induction, we have two steps. One, we want to prove that you can knock over the first domino. Then, secondly, if my Apple Pencil would work, secondly, we want to prove that there are no gaps. So secondly, what we're going to do is just imagine that there's some number all in a row. There's some number all in a row, and therefore, because we knocked over the first one, we knock over a bunch. Now, I have no idea where we are. This is the nth math book or the nth domino. If I can show that there is not a gap to the next one, everything is getting broken here. So the nth, yeah, so if the nth, we assume that that n of them are close together, then I want to show that there is not a gap to the next one, that the gap is small. This didn't work at all. I should have practiced that. Oh yeah, I meant to delete these occlusions because I knew this was going to happen. Oh well, whatever. So what we want to prove as our next step in induction is that there is no gap anywhere. I have no idea. This could be the 4,000th domino or math book. But whatever it is, the next one is always close. And if there are no gaps anywhere in the universe of numbers, then Luna just knocked over every infinite math book in the universe, and she's very, very happy. So, let's see. Let's make this slightly more formal. I don't remember what the hell. Here, this one? Okay. So, to make this slightly more formal, we want to show that a proposition, a mathematical sentence, is true for the first number. Usually the first number is n equal 1. Then we know, so this is the idea that Luna can knock over the first one, that you can knock over the first domino. The proposition is true for at least one number. Then the second step is something that we call the inductive hypothesis. Let's assume that it holds up to some number of dominoes or math books, And our goal is to show any time that the claim is true for a number, for any number, then it's also true for the next number as well. Then that proves that all of the dominoes are close together. Luna knocked over the first one. They all fall down for every single number in the universe. This relies on something called the well-ordering property or something or other. I don't want to get too technical about it, but this is the strategy. There's two steps, the base case and then the inductive step. Okay, so let me know, please, in the comment section, how was that? Are you with me still? Because this is my first time ever trying to teach this material, and I've got a lot of people watching, so feedback is a gift. All right, now we get to revisit Gauss's proof again, which is so cool. I didn't tell you we're revisiting Gauss's proof twice. I like to imagine that after he found his clever argument, he scribbled down and figured out another argument. He was really good at finding multiple arguments for the same incredible math fact. I think he proved quadratic reciprocity many times throughout his career and just kept finding more beautiful arguments for the same math fact. So as a kid, I think this is what happened. Our claim, we want to claim that the sum of the first n numbers is n times n plus 1 divided by 2. This is our claim. Our base case is true because the left-hand side, if you substitute n as 1, there's only one number in that list. It's 1. And then the right-hand side is 1 times 2 divided by 2. So, we're done. This is enough. Usually the base case is easy. It's almost trivial. A lot of math books will say the base case is trivial or something. It's kind of rude, but in this case, the base case is true because 1 is the same as 2 divided by 2. You substitute concretely the number 1 into the left-hand side and the number 1 into the right-hand side of your claim. Now, for the inductive step, as I described, we want to assume that it's true for n numbers. Let's assume the claim is true for n. We want to show that it's true for the next number as well. Like, when it's true for n numbers, then it must also be true for n plus 1. So, pause the video. What would that mean? What exactly is your new goal in this proof? What is the goal? The goal on the left-hand side is that the n plus 1th numbers added together, that's the left-hand side. And then substituting n plus 1 into the right-hand side, it would be this. N plus 1 times the next number, n plus 2, divided by 2. So this is our goal. We want to show that this is true if we assume the claim. Now we want to do this type of proof. Left-hand side equal ... right-hand side. So we start with the left-hand side, and by associativity, we can add the first n numbers and treat that. We can put parentheses around the first n numbers. Then, using the inductive hypothesis, because we assumed it's true for n numbers, then that first part is n times n plus 1 divided by 2. That was our assumption. And then I also noted that we can just write n plus 1 as 1 times n plus 1, because any number is 1 times itself. Then I can do distributivity, and I can rewrite 1 as 2 divided by 2. Then, I stopped writing the yellow parts, I guess. Then, and most math books in a proof like this, you at some point you stop writing every single justification. So it's not like proofs in geometry where you have a table and you must fill in every single detail. In a math proof, in a real math proof, you start writing the steps without always justifying commutativity and associativity or something. So I can add two fractions. I know we haven't introduced fractions yet, but you know what a fraction is. Or if you don't, here's your chance. Go back and read the section on rational numbers. That's fractions. Then I used distributivity. Then I added numbers together. N plus 2n is 3n. And then I can factor that numerator. I can factor it this way. If you don't believe it, you can start from the right-hand side and use distributivity like we've used before. We've done problems with two binomials, and you can see that it equals the previous thing. Thus, when the claim is true for n, it is also true for n plus 1. So we are done. When the proposition, the reason that I'm using P everywhere, when the proposition is true for n dominoes, there's no gap after it, and it's true for the next domino as well. And then that works for every number, so therefore Luna has a lot of fun knocking over every single domino, every single math book in the entire universe, knocking over every single mug of coffee. That dang cat. Thank you. That's it. We are just a little bit over time. I'm shooting for 40-minute videos. We're 100% live right now. I wonder if anybody's still here in the chat. Thank you everybody for watching. Math can be a hobby. Discord.jcpractices.com and feedback. Thank you all for being here. Leave a comment in the comment section. What did you like? What did you not like? What would you like to see more of or less of in the future? I can only build something awesome if I get feedback from people and I know what's working and what's not working. So if you enjoyed this, please leave a comment, join the Discord, and share the playlist, dude. If you haven't seen the other videos, that first URL is just a way to get to the playlist. It's very easy to type, very easy to remember, very easy to share. So mathcanbeahobby.com just takes you to the YouTube playlist. Now, special thanks to all the people who are helping make this be possible. Special thanks to all these people, to all the channel members, dude. Like, I just cannot believe, dude, it's amazing. So I want to do this at the end of every video. It's kind of like Patreon walls. Like, I'm using channel memberships on YouTube, and I'm just so grateful to have the opportunity to do what I'm doing right now. So thank you, everybody. Appreciate it. Take care. Bye. I'm going to stop the recording and see if anybody's still here in the chat. I hope you all enjoyed it. Bye. Bye. And I promised that Luna would be in this video, right? Even though she's sleeping, she's still going to be in every video one way or another. Thanks for watching. Bye.